With hindsight, we probably shouldn't be so surprised at the huge success and mass proliferation of mobile apps because many factors came together to fuel their massive growth. For starters, the smartphone became not just ubiquitous but essential, such that owners not only always had their phones with them, but they also rarely went for more than a few minutes before checking for notices, updates, and likes. This lecture summarizes the security issues brought on by always on, always connected, and ever present smartphones, smart home, smart building, and smart city devices that now number in the tens of billions. This lecture also provides an overview of the many wireless protocols that support varying use cases. A notable feature of mobile apps was their single purpose, as opposed to web-based applications that were designed as Swiss Army knife style apps. Instead, native mobile apps were designed to do a single thing, and to do it easily, and to do it well. The advent of vendors' own app stores, which authorized, authenticated, and verified apps, made it easy for users to safely download apps with confidence. Also, the app stores allowed developers to easily publish their mobile apps and earn revenue when users downloaded the apps to their phones. From the developer's perspective, easy access to software development kits, or SDKs, and the low development costs combined with the ease of publishing made mobile apps development a very profitable alternative to developing and marketing desktop apps. The huge security problem that was bound to follow the meteoric rise in mobile apps adoption came about through the combination of too much functionality and too little user security and privacy awareness. This was simply because developers could request access programmatically to any function regardless of its relevance to the application. The operating system, or OS, would police these actions and seek explicit permission from the user before allowing the app to use the features, for example, the GPS, camera, or microphone. The problem was not the technology itself. The issue was that users simply granted permission to the mobile app without any consideration as to why it required that particular functionality. The result was a disaster for user privacy, but a field day for developers who harvested user personal data and then sold it to advertisers. Worse, many mobile apps were actively spying on the user or stealing their data and contacts for nefarious purposes. There is no reason that can justify having a flashlight app collect GPS data on your whereabouts other than selling it to researchers, advertisers, or political interests. Most people, if asked, can a random company track your whereabouts at all times for free and profit by selling it to third parties with no restrictions on their use of that data, would likely give an emphatic no. Yet, for years, this is exactly what millions of people were allowing. The threat of malicious mobile apps was countered by the major app stores because they diligently checked all uploaded mobile apps for unjustified feature requests, and this ensured that most never made it to the market. However, the manufacturers can only do so much, and the onus for security and privacy remained with the end user, and this is where customer security awareness became so important. The modern smartphone resolved many legacy communication issues and filled a lot of the gaps because it was a true multi-channel device. This was because they could support not just voice calls, but SMS messages and email. The advent of Voice over Internet Protocol opened up new wireless channels such as online chat, presence detection, and mobile to Wi-Fi handover. Indeed, the concept of unified communication was built upon the merging of distinct wireless technologies into one omni-channel communications platform. Today, those advances in mobile wireless technologies now allow us to be found and followed wherever we go. Further, by placing this communication platform, a virtual private branch exchange, or PBX, in the cloud enables communications that are truly always on. Further, the confluence of mobile or cellular technology with Wi-Fi, voice over IP, Bluetooth connectivity, and cloud omnipresence, all features that are common to the smartphone, allows for multi-channel communication anywhere, anytime, and on any connected device. Unified communication brought the vast potential of communication, collaboration, productivity, and business application integration to the masses, but it came at a price: security. Despite heralding an era of tremendous convenience and efficiency, wireless unified communications came with its own Pandora's box of wireless security issues brought about by this newfound gift of mobility. As we have seen, a smartphone could provide the user with a multi-channeled communication device, which meant they were no longer tethered to the office or home telephone. The mobile revolution heralded the era of secure remote computing, along with the tremendous advances in mobile carrier broadband and Wi-Fi technologies it rode upon. Now users could safely and securely access company computing resources and servers from anywhere, at any time, and from any connected device. This freedom of access to resources fueled development and innovation. However, it also tore down the concept of traditional network fortification. Prior to the mobile revolution, networks were designed with traditional layers of fortification in place. The mobile revolution changed everything because now every user wanted to be mobile and working on their personal devices. Importantly, if everyone wanted access at any time, from anywhere, and on anything, it made the geographical centralization of computer assets behind a fortified barrier pretty much redundant. Clearly, architectural changes were needed. Mobility brought about a systematic change in how applications were developed and presented to users. In traditional networks, business software tended to be client-server or service-oriented architecture. These monolithic applications were unsuitable for mobile users who required either native mobile apps or web-based applications that they could access over the internet from their devices' browsers. By 2010, businesses of all sizes began to see the benefit of cloud computing, especially with regards to mobile and wireless applications. This was because it soon became clear that mobile and wireless technology perfectly complemented each other. Hence, a hybrid style of mobile application appeared that was inherently native with a local user interface but utilized application programming interfaces or APIs on cloud-based applications for their processing, intelligence, and functionality such as Google Maps or Yahoo Finance. Cloud integration with mobile apps came thick and fast because developers could now build mobile mashups or collections of external API services linked together with some code to easily build highly functional and often very complex applications in minutes instead of months. However, the trouble was that rapid development and deployment almost always augurs badly for security, and it was no different this time. The result of the early cloud bonanza in cloud and mobile integration via mashup applications was unsecured data communications that resulted in loss of data integrity and privacy. Nonetheless, the advantages of mobile and cloud integration were indisputable, particularly for mobile developers and the workers who use these apps. This rapid change in the IT landscape revolutionized the way IT approached security. Gone was the traditional fortress mentality, with its insider and outsider approach. Google first published the Zero Trust model in 2016, which explained how the tech giant considers both internal networks and external networks to be completely untrusted. This new decentralized authentication model was quickly adopted throughout the enterprise, industry, and commerce as a blueprint for cloud and hybrid architectures where on-prem, cloud, and software as a service infrastructures coexist. Some advantages to moving to a cloud security zero trust solution were clear because now onerous security tasks such as single sign-on, firewall rules, as well as robust identity and access management could be outsourced to a cloud provider, as could server maintenance and operating system administration. Indeed, all that remained that was necessary was to ensure data on the user's device was stored securely, and communication was done via Hypertext Transfer Protocol Secure, or HTTPS. In only a few years, business networks changed dramatically from being centralized data centers built as castle and moat structures to being focused on cloud-based architectures utilizing the zero trust security model. Over the last decade, cloud computing has emerged as a major disruptor in enterprise security architecture. Businesses of all sizes have shifted operations away from the data center toward the cloud. Cloud architecture provides a convenient, efficient, and often cost-effective way of hosting applications over the internet. The cloud model also brings on-demand, as well as self-service access to virtual and physical computing resources via the internet, delivering true anytime, anywhere, on anything style computing. Cloud-based architecture has many advantages. One of the main advantages of the cloud is to provide the users or clients with easy access to business applications and a huge amount of information from anywhere that has an internet connection. However, with ease of access and all that confidential on the cloud, the biggest concern today is with security and privacy. When we refer to mobile cloud computing, or MCC, as opposed to the more generic cloud computing, we are focusing on the distinct combination of cloud computing, mobile computing, and the wireless network. All of these functions are required in order to bring the vast amount of cloud-based computational and storage resources to mobile users. The basic concept here is to make it possible for cloud-based mobile applications to be executed on a vast array of diverse mobile devices. When designing mobile apps, a key design criterion will be whether to deploy the app as a mobile cloud app or as a native mobile app. Therefore, we need to consider the differences between the two. On one hand, we have native mobile apps, and these are designed specifically for the type of user device, such as the operating system version, because it will be installed and run directly on the device. As a native mobile app is device/operating system specific, then a different version will need to be created for each of the mobile devices/operating systems supported. A native mobile app is typically downloaded from an app store. Mobile cloud apps, on the other hand, are more like web-based applications because the application runs on external servers and not on the device itself. This means the app is device/operating system agnostic because it only needs a browser on the mobile device as the user interface. Wireless technology has developed over a long period, but really has transformed over the last couple of decades as new use cases have emerged. Back in 2000, hardly anyone in business used Wi-Fi 802.11b, other than as a stopgap for a lack of wired Ethernet. However, success in the consumer market came quickly, and Wi-Fi was on its way by 2005 to usurping cabling and the connection of choice in the home and the office. The huge spike of interest in Internet of Things in consumer and industrial services brought the need for wireless technologies and protocols that addresses specific use cases. These new wireless technologies would have to work with resource-constrained devices and/or be able to share resources across an ad hoc mesh network. Among other things, these IoT use cases needed to work over low power, have much shorter or longer range, and support low data throughput. They also had to cater for a vast range of potential use cases in industry, healthcare, commerce, and even in oil and gas. A notable lasting effect of the mobile revolution was the emergence of new wireless technologies that met the requirements of diverse industrial and consumer use cases. Over the last couple of decades, many innovative wireless technologies have come to the fore to meet the specific requirements of, amongst many others, Internet of Things, machine-to-machine or M2M communications, global communication systems, and even ultra-long distance space travel. These can all be considered to be applications of industrial IoT, and the one thing they have in common is that they have specialized operational profiles. To meet the specific challenges thrown up by the emergence of IoT in consumer, commercial, and industrial scenarios has required a complete reimagining of wireless technologies and protocols. A vast array of specialized wireless technologies and protocols have emerged that can operate on resource-constrained devices in order to meet the challenges that these new use cases present. The latest research and development is focused on low-cost, low-power wireless connectivity solutions. There are, however, serious trade-offs that need to be taken into consideration. For example, if the goal is higher data rates, then this requires higher power levels to enable the radios to transmit these higher frequencies. As a result, designers tend to opt for lower frequencies to conserve and optimize battery life. However, lower frequencies mean slower data rates and longer transmission for the same amount of data. This means that the radio will stay on for longer, thereby consuming more power and potentially draining the battery. One of the early IoT enablers is the low-power IEEE 802.15.4 standard. It was first introduced back in 2003 and updated to and including 2012 to set the standards for low-power commercial radios and wireless personal networks. The 802.15.4 standard can be used with IPv6 over low-power wireless personal area networks and standard Internet protocols to build a wireless embedded Internet. The advent of a plethora of wireless communications over the last 2 decades has been one of the drivers for adoption of Internet of Things, both by the consumer and in industry. The array of wireless technologies has arisen because they serve different purposes. Some technologies, such as Wi-Fi or 802.11, are designed for high bandwidth and throughput where power was not an issue, for example for web browsing and downloading from the internet to a computer. Bluetooth, on the other hand, was designed to provide wireless connectivity in a personal area network. It became hugely popular by connecting the devices that you wear or carry, such as a smartphone or a watch, to a headset. Zigbee found a niche in the smart home market by proving to be adept at interconnecting devices from different vendors around the home. As a result, Zigbee has a range and capabilities that fall somewhere between Wi-Fi and Bluetooth. Today, wireless communication technologies and protocols are constantly evolving or being repurposed to match new use cases. Zigbee has, for example, evolved to cover neighbor area networks in industrial IoT scenarios, and Bluetooth's range and capabilities have also improved beyond the scopes of the PAN. Whichever technology we choose to adopt will always have constraints, such as range, throughput, power, physical size, and costs. When you deploy in the cloud, there will be the obvious decision as to how you will securely connect to the cloud infrastructure from your wireless devices, networks, or environment. The common choices are to use the cloud service provider's VPN or interconnect configurations. These may be direct or supplied via a third-party carrier, but either way, in the case of interconnects, the data must be encrypted. This is because many third parties just provide a communications channel. It's up to the business to encrypt the data as they see fit. Free space optics, or FSO, are laser wireless broadband WAN links that have a range of 3 to 5 kilometers line of sight and a throughput of 10 gigabits per second. These laser beam point-to-point links are used for data backhaul from remote offices, enterprise, or campus networks, or, more recently, within remote IoT sensor networks. WiMAX is an alternative last-mile solution to carrier networks, long-term evolution, or LTE, and digital subscriber line, or DSL networks, because it is a high-speed radio frequency microwave technology that provides up to 1 gigabit per second bandwidth. A very small aperture terminal, or VSAT, is a satellite communications technology used to deliver broadband internet and private network communications over a vast coverage footprint. When you need to connect to the internet, when you are hundreds or even thousands of miles away from a base station, or you need to broadcast to clients over an entire continent, then satellite wireless communications is the solution. As we have seen, there are many diverse methods for wireless WAN communication, and each has its own properties and challenges. This is one reason why SD-WAN tends to aggregate several diverse wireless technologies into the mix to ensure robust network configuration regardless of the weather, geographic, environmental, or atmospheric conditions. By extending SD-WAN into the wireless network, it enhances network performance while improving security for all types of on-premise and cloud-based applications. IoT encompasses such a broad spectrum of industries and use cases that no one low-power WAN technology will fulfill every use case requirement. Therefore, several technologies have emerged that offer different choices, and sometimes these are trade-offs between range and throughput, or battery life and operating frequency. However, each technology has its own set of attributes, so it should be possible to find one that matches requirements. Sigfox low-power WAN is an end-to-end system consisting of the presence of a certified modem at one end and a web-based application at the other end. LoRaWAN, or Long-Range Wide Area Network architecture, is a star of stars topology whereby end-node devices connect through gateways to network servers. The LoRaWAN protocol is based upon a chirp, which is a spectrum spread wireless hop between the end nodes and the gateway. Wi-Fi 802.11ah, or HALO as it's more commonly known, operates in the ISM bands, or industrial, scientific, and medical radio bands, just below 1 GHz, because these lower frequencies enable battery-operated equipment because they use low power. While most Wi-Fi 802.11 have maximum ranges around 100 meters, HALO can reach up to a kilometer radius with the right antenna. Millimeter radio undoubtedly has the potential to send high throughput, but it will be over short distances, less than 1 kilometer. It will need to be with a clear line of sight. However, there is another operational problem. Millimeter radio is highly susceptible to not just objects in its line of sight path, but also atmospheric conditions because it is susceptible to even light rain. In adverse conditions, millimeter radio requires a high power boost to overcome the rain fade margin, and that would rule it out for most IoT purposes. There is a definite requirement today for large-scale wireless LANs. Nonetheless, the present capability of Wi-Fi to meet that organizational need is very limited. As a result, many organizations are moving away from Wi-Fi toward adopting private LTE. Private LTE has emerged in recent years as a solution to fill the gap between high-end private Wi-Fi networks and public LTE carrier networks. The advantage of a private LTE network is that it can deliver dedicated, fixed-cost connectivity and better information security for all IT assets and IoT devices. Private LTE, just like carrier LTE deployments, uses licensed, shared, and unlicensed radio frequency spectrums to reduce costs, congestion, enhance traffic flow, and ultimately to improve information security. The private LTE network replicates, on a smaller scale, carrier LTE networks and is built upon micro towers and very small cells, making it similar to a wireless LAN with its access points. Private LTE can deliver specific benefits such as lower data costs, improved network performance, and tighter information security. The way that private LTE provides these benefits is that it works over different frequency bands, from the saturated 802.11 Wi-Fi networks. This is hugely beneficial in industrial use cases where keeping the competition for available frequency and potential RF interference to a minimum is essential to the running of critical autonomous devices such as robots. However, the benefits of private LTE are not just about frequency separation and isolation. It also comes about through its ability to handle priority, preemption, and its inherent capability to scale. This means that private LTE networks can handle vast amounts of locally attached devices and their traffic without having to go out onto expensive pay-per-bit public carrier LTE networks. Finally, private LTE is considered by many organizations to be the ideal stepping stone to 5G. Historically, wireless LAN technology has been viewed by security professionals as convenient, but an inherent unsecure medium. This is because early wireless LAN implementations, often found in small office/home office or SOHO environments, were typically installed by technicians who were not knowledgeable about radio technology or security. The result was unauthorized users poaching the network, that is, using its bandwidth without permission. Worse, some users would gain unauthorized access to the data on the network, even injecting or forging data. Another risk with wireless networks is intruders using directional antennas to eavesdrop on the network, even from quite some distance away. With these problems in mind, the IEEE set out to develop a security standard as part of the 802.11 standard. The first attempt was called Wired Equivalent Privacy, or WEP, used a challenge/response mechanism. Unfortunately, an eavesdropper could intercept the challenge and response. In response to WEP's inherent weaknesses, the Wi-Fi Alliance introduced Wi-Fi Protected Access, or WPA. It too was short-lived because it proved to be only more difficult to break. However, its success for Wi-Fi Protected Access 2, or WPA2, did become the standard for many years. WPA3 was first introduced in 2019, which has more advanced features to accommodate today's business and industrial security requirements. In the early days, mobile phone manufacturers made instant and easy access a higher priority than basic security. As such, smartphones and tablets were enabled for Bluetooth discovery out of the box. The criminal element rejoiced, because they now had direct access to these devices, which they could surreptitiously use to make voice calls, send data, listen to or transfer calls, gain internet access, and even transfer money. Today, mobile phones are no longer shipped with Bluetooth enabled in discovery mode. In addition, security has been hardened to prevent unauthorized connections and remote access to the phone's features. Confidence is such that smartphones are trusted for use in e-banking, e-commerce, and email. However, despite these improvements in securing wireless mobile devices and the underlying radio networks, there is no room for complacency.